So what we're going to do today is to try to wrap up the discussion on decision trees and ensemble methods, which are widely popular methods when we are dealing with machine learning. And then we are going to, after that, we are going to start looking at another very popular method, which is called support vector machines. And support vector machines has been within the family of machine learning methods since the end of the 90s in the previous millennium. And it's a method which is widely popular, but it's also a method which has its limits due to the fact that it's essentially, it ends up being a convex optimization problem, which means that you have to be able to deal with the matrices and be able to store them and compute with them. So what I wanted to bring up now, just a quick reminder of the boosting methods, which we started to look at yesterday. So these boosting methods are methods which you can think of as weak learners, and where you keep improving upon the weak learner gradually in an iterative way. So you would start with a method which could be normally a decision tree, and that's the typical entry level for these boosting methods. And then you would have a decision tree which perhaps doesn't do better than just slightly above 50-50. So you could get a accuracy, if you're doing a classification problem, an accuracy of something like, let's say 60%, which nobody would be happy with. And then you can keep improving upon that. And what we saw yesterday when it came to boosting was one method which is called adaptive boosting, or AdaBoost, which has been tailored to classification problems. But we looked also at the regression type of problem. And the basic philosophy of all these methods is actually to, if we now go back to the Jupyter notebook here, and we look at the regression case. So the basic philosophy is actually to find a function where this function B is some weak learner. So this could be a shallow decision tree, which is easy to train. And then in an iterative way, so in this case you would have m iterations, you would keep improving upon the final function f of m. And f of m is then your model, the best possible model you can provide us with. So for the regression case, this could be a simple polynomial if you wish to do that. But in general, it's normally replaced by a decision tree. And then it's a decision tree for regression. And when we looked at the classification case, there was a specific way by which we defined the cost function, and that was in terms of an exponential, which then emphasized the errors which we made. And every iteration, we put more and more emphasis with a weight on those results which led to a misclassification. And then gradually, when we moved on, even though we put more and more weight on the misclassified results, we ended up with a result which is pretty close to almost 100% score. So AdaBoost is a widely used method, but what we did not cover yesterday was gradient boosting, which is actually perhaps nowadays the most popular boosting method. And when we've gone through the algorithm for that one, what we're going to do then is actually to wrap up our discussion of decision trees and ensembles before we move on to support vector machines. Sorry for that. So as I said yesterday, we went through the adaptive boosting. And what we are going to do now is to switch back to the whiteboard and look at the final method. And then we are going to refresh the memory again by looking at some calculations. And the library which is widely used is called extreme gradient boosting. And as I mentioned yesterday, this is a library which tends to win many classification competitions. But the missing piece which we had was actually gradient boosting. And what I wanted to give you are essentially the elements which will allow you to be able to write your own gradient boosting code. And as you saw yesterday, both for the adaptive boosting, whether you did regression or classification, the basic steps are pretty simple. And if you don't want to write your own decision tree code, you could actually easily write your own boosting code by simply calling a decision tree. And if you do a given number of iterations, what you actually are doing is you're constructing an ensemble of trees, and every tree will be slightly different. So let's look at the gradient boosting, which is perhaps one of the more popular machine learning methods, in addition, obviously, to the whole battery of deep learning methods. So the basic philosophy, again, is that we want to have a function f of n, which is our final model. So m doesn't stand for model, but it stands for the number of iterations. And if you're using a decision tree, you can think of every single iteration as you producing a new tree. And then at the end, if you do 200 iterations, you would have a forest of 200 trees. So this is now given by some sum over I equal 1, and you made a guess for f0, and you would have typically some parameter. This is what we did yesterday. We had a parameter b of I, and then we had we call this beta of I, not b, but beta. We have a beta of I, and then we had some function b of I, which in principle is our weak learner, but it gets improved in every iteration. So this depends then on some additional parameters, beta of I. So the basic function which we are going to look at now is slightly different, but not that different. And in the previous case, what we did when we improved upon the function, so when we did this kind of iterative machinery, what we had is that we had the f of n at a given iteration n was given by the previous value plus the optimized parameters beta n times this b of n, which then depends on this parameter gamma of n. And at every iteration, we had an optimization stage. And in the optimization stage, we would calculate the derivative of the cost function with respect to these parameters beta and n. Now, when we now go to gradient boosting, the philosophy is going to be the same. But with gradient boosting, what we are going to do now is to replace what we have with a gradient. And let's see how we can do that. So we are going to make an assumption now that our function f of n here is going to be given again by the previous value, but now it's going to contain a parameter which I'm going to call gamma of n, and this is multiplied with a function Rm of x. And I have to define to you what this Rm is going to look like. So this R of m is actually going to be defined by a gradient, but if you now look at a simpler case, so what we have defined previously is a y of I tilde. So let's look at the basic elements here. And this is going to be this f of x of I, which in our case is going to be an f of m. This is the final model. So f is now a function which replaces what we normally have called our model in terms of a y tilde. And then we have the observations. And if you now think of the regression case as an example, so let's illustrate what's going on using regression as an example, which is often a little bit easier to demonstrate and to get a kind of feeling of what it is. Now, what we are going to do then is actually to define a cost function. So we're going to have a c as a function of f, and that's going to be equal to our standard function, which we have seen many, many times. So we have the mean squared error, and we have y of I minus f of x of I, and this is squared. Then we are going to define the value which we get at every iteration is now going to be given by this y of I tilde. So it's going to be an f of n of x of I, and this is going to be given by f of n minus 1 of x of I. But now I'm going to put a subscript I on this term gamma, and this term r, and this is given by a gamma m here. Now, this r of m, or im, is now going to be defined as y of I minus f of m at every stage in terms of the difference between the values we want to reproduce and the model which we have made. So this is the way we're going to define. So you can think of this as a residual, which expresses how well your model is doing. Okay? That means that when you look at the cost function then, if you now think of the derivative of the cost function with respect to this function f, so if I take my c of f and derivative with respect to f, this is going to be equal, if I now take the negative of this function, so let's just take the negative because then we get rid of this sign. So we have a 2 over n, and if you now take the derivative, and now we are going to look at this calculated for a specific I. So we are singling out that one. So if you look at the sum, which you have in the cost function, we are now just picking one of these values. So if you take one of the derivatives, this is simply going to be y of I minus f of x of I. And this is nothing but 2n times n, and then I have this function Ri of m. So this is my residual at every iterative step here. Now, my function f is going to be defined in terms of this parameter gamma as well. So when you look at the algorithm for the gradient boosting, it's going to use these ingredients. It's going to need the gradient, but then it's also going to optimize the cost function with respect to this parameter gamma. So let me set up the algorithm for gradient boosting. So what you typically need first is obviously to define your domain of data. Define D, which then contains your input and output values. You have an x1, y1, xn minus 1, and yn minus 1. So this is our data set. Then the next thing we need to do is actually to define the number of iterations we want to make. Define n, which again is going to define the number of times we take the derivatives. And in a certain sense, when we make a connection with adaptive boosting, this is something which would define the number of trees which we're going to grow in order to find the final value for the function f. Then we need to define a differentiable cost function. And you've probably seen that many of the cost functions which we have are functions which are differentiable. One of the reasons why we opted for the mean square error is that its derivative is pretty easy to compute, and it's a differentiable function, which also has the benefit that in some cases it gives us analytical results. Then I also need to initialize, and the way I'm going to do that, so this cost function is a function which I'm going to define in terms of what I call the loss function. So this runs over all the data set which we have. So this is going to depend on y of I, and it will depend on fx of I. Then I'm going to define or initialize my function y, my function f. So the next case I need to do is to initialize my function f, 0 of x. And the way I'm going to do that, since my f is now a function which depends on this parameter gamma, as you could see. So if you go back here, my function f now depends on this quantity here. So I want to initialize it, and you see now that there is going to be a residual here. So we could give a guess on that one, but we're going to optimize it so that we get the parameter gamma. So that means that we are going to optimize, or by initialize, f0 by optimizing What we are doing then, we optimize f of x0, and that's going to be an argmin with respect to gamma of this sum over the different contributions to the cost function. So as soon as I have the gamma, I will have an initial guess for the residual in addition. And as soon as I have this gamma, then I'm ready to start the iterative process. You could actually, as we did with ADA boost and the normal adaptive boosting methods, we could have defined this f0 to just be 0, or just give it a random value. So you saw that when we looked at ADA boost, it was pretty common to actually set f0 equal to 0. That's a common choice. Or you can just give it a random value. That's also possible. But then, what comes now is our loop for I or m equal 1 up to the final iteration, which we're going to do. Then we are going to compute, the first thing we do is to compute the derivative. And this quantity Rim is going to be the gradient of the cost function with respect to the function f. So I take the derivative of y of I, f of x of I, with respect to df x of I, and this is evaluated at f of x of I is equal to the previous value which we calculated. So just keep in mind, so this would be something like what we put up here. So here we have the function, and if we want the derivative with respect to f, we would actually get this function here. So this is defined exactly like that. So it's easy to see this from the linear regression, what this derivative is going to be. So this is a kind of residual, which we are calculating, and we are doing this for all I from 0 up to n minus 1. Then the next step is to fit. So we have now a function which we want to fit, which is our weak learner. So fit the base, which is normally a weak learner. And normally this is a decision tree. And when I say weak learner, this is normally, in most of these applications, it's actually a decision tree. And using the training set which we have. Set for all I, again, 0, 1, up to n minus 1. So that means that we have now computed the residual. We have a weak learner, which is the entry point which we use to start the iteration with this function. And then we train that one. So we have a result from our decision tree. And with the decision tree, then we go back. And the next step is actually compute this parameter gamma. Compute the multiplier gamma m, which in a certain sense plays the role of a kind of learning rate. By solving, by optimizing, the parameter, so we get a gamma m. This is the optimal for that specific iteration, and that's an argmin of gamma, And then we have a sum over all the contributions to the final cost function, which is now given in terms of y of I. And then I have my function in here, the argument f minus x of I, plus this gamma of Rm of x of I. When we have that, then we update our function. Then we have an update, which is fm of x, which is now equal to fm minus 1 of x, plus this gamma m multiplied with Rm of x. And that's end loop, and then we return the final model which we have evaluated for all values I from 0 to n minus 1. So this is the basic step of gradient boosting. So what we're doing now, compared to the previous cases, is that we are trying to find a function representation which is not generated at a specific point, like we discussed yesterday with steepest descent, but it gives us a function representation of this specific model which we have in terms of some kind of weak learner. So the basic steps are actually not that difficult to implement, as you can see. The only thing you need to have at the bottom is a weak learner. And that could be a decision tree, or if you're doing a regression problem, you could even plug in a simple polynomial. So if you feel tempted for the final project to actually look at the development of decision tree algorithms from a single tree to, let's say, an ensemble of trees, this could be one possible path in project number 3. And then you could clearly look at the complexity of your model. It's as a function of the number of iterations you would do, which again corresponds in boosting to the number of trees you actually grow. If you do a random forest, that would simply be the complexity of the model would be the number of trees you deal with and how deep the trees are. If you do a bagging method, that would also be the number of trees and the level of the tree which you produce. So, as we saw yesterday, these methods are extremely powerful. They are intuitive and they are easy to implement. There is not much deep mathematics behind what we are doing, except calculating gradients and doing the optimization. So if you look at the last optimization problem which we have, this is something which you now probably are pretty familiar with. We have done that with the gradient descent. So this again would be a kind of gradient descent approximation. So you would evaluate these gradients with the autograd or your own function for the gradients, and then you would simply improve upon the values of this gamma m till the gradient vanishes. So that would be the typical optimization problem you would end up with here. And then you need to calculate the gradient as a function of f at every iteration here in order to estimate the residual. So I hope you like these simple models. I am pretty fond of them. There's not much deep mathematics, and there's a lot of possibility to play around with different types of cost functions. These are kind of low-level methods. Well, I perceive them as low-level methods, but they are very intuitive, and decision trees have the advantage that they are explainable, even to somebody who does not know what goes behind it. So let's take a quick reminder of what we have done before we move over to support vector machines. So what we have in connection with decision trees and ensembles. So we started with decision trees. And when it came to decision trees, the algorithm which we discussed for splitting the tree, so we opted for a binary split. They are easy to explain. You can easily make the tree, and every branch you have and every node has a simple explanation. So you have a binary split, and we use something which is called the CART, which is the classification and regression tree algorithm. And in this algorithm here, for classification, what we ended up with, we used either the Gini factor or the entropy in order to make the splitting of the different nodes. Gini factor or the entropy. These are the most common options, and you will see that when you use, let's say, scikit-learn as a library, you can actually plug in whether you want to use the Gini factor or the entropy. Now, the entropy is something which many of you are familiar with, and you know that if the entropy is high, you're actually having a high degree of mixture between different types of cases, and you're looking at the less likely cases. They are emphasized, whereas the case when all the data look the same, then the entropy is 0. And you use that one as a way to choose what is your main node, and then you take the remaining data, you find the next main node, and so on, till you actually end up with a pure case where the Gini factor or the entropy are 0. And they define what's normally called the leaf node. So decision trees are very easy to use. They are easy to implement, but they have the problem that even if they give these nice explainable features, is that they can easily lead to overfitting. It means that you will often have a high variance. You can compensate with this by looking at the ensemble methods. And these ensemble methods, these are methods where you are not constrained to use a decision tree as your weak learner. So there is a set of weak learners which you would use. They often take that as a starting point, weak learners. And then you try to improve upon that by either a kind of iterative sequence, or you could just build up a forest of weak learners. So one of the typical models which are used is bagging, which is actually a bootstrap aggregate. And we went through that last week. And this is normally called shortened to bagging. So in principle, this leads to a homogeneous forest. And you simply need to decide how big the forest should be. Then the next step, or the next method, is a random forest, which is also widely popular and extremely easy to implement. Random forest tends to have a pretty low bias variance, as we saw in these simple examples we ran through last week. The same also with bagging, but bagging has a problem that there may be stronger correlations between the trees because you're using the same data set to find what is a root node, which means that essentially all trees will basically have the same root node. And that leads easily to trees which become lookalikes. And that means that there will be correlations between the different trees. Random forests, on the other hand, picks randomly only a subset of your features. So if you take all the features and you calculate the Gini factor or the entropy, there is always the risk that your tree will be dominated by some main feature. And that will pop up again and again. So a way to decorrelate your forest is by picking randomly a subset of the total features. So if you have 100 features, perhaps you pick only 10 of them. And then you compute the Gini factors or the entropy, or if you're using a regression, doing a regression analysis, you would then just subdivide the regions till you have reached the top level of the tree. So random forests, what we could say now is that this is a heterogeneous. So this is a forest of different trees. And then we have the different boosting methods. So we have adaptive boosting, which we discussed yesterday in more detail, and how we can do both classification and regression. So essentially there we take a decision tree as input, a weak learner, which means a shallow decision tree, and then we keep improving upon that. So that was the adaptive boosting. And then we have the gradient boosting. We discussed also voting methods, but they are actually being less used. And I should say that gradient boosting is the one method which many, many practitioners now actually end up using. And I just wanted to repeat some of the results which we looked at yesterday. So these are the basic methods. So if you feel free to have that as an alternative project tree, where you actually go through these different methods. You can look at the bias variance trade-off for these methods and analyze that as a function of the tree depth, as a number of trees, etc., etc. So that's always a useful exercise. And that book of Hasty, Tishbarani, and Friedman, chapter 10 has actually a very nice description of the statistical analysis of these different methods. So as I said, this is a whole class of methods which is forms a widely popular set of inputs to machine learning. So let's just quickly remind ourselves a little bit of some of the results which we looked at yesterday before we move over to our next topic, which is going to be our last supervised learning example, which is support vector machines. So we had examples yesterday where we looked at adaptive boosting, and the kind of case which we looked at was a classification problem. And in that specific case, we looked again at the cancer data. And in this particular case with adaptive boosting here, we have a decision tree classifier. So this is the basic method. You could have replaced that one if you want with another classification. You could have placed in logistic regression if you wanted to. And then with the max depth tool, we perform 200 iterations or 200 estimates. We need a learning rate when we calculate, when we do the optimization at every stage. So every stage, there is an optimization part where we need to calculate gradients. So that means that we need to feed in a learning rate. And in this particular case, we got a pretty good description with adaptive boosting. At the end of the slides, what I've added, so I'm just going to scroll down to the very end here. There is an example on using XGBoost on the same data set. And as I said, XGBoost is a library. It's a library based on gradient boosting, but it's a highly streamlined library, which is extremely efficient. And this library is available. You just need to install XGBoost on your laptops or your PC. And in this case, I define not in the regression case, but I'm looking at the case here, which is my classification problem with the breast cancer data. So again, we split into test and train as usual. And then there's a fitting here. And then I make the prediction with the gradient boosting or using this extreme gradient boosting library. And as we saw yesterday, this gives a pretty good description of the data. So we have on a true positive and a true negative, we have 100% classification on the test data. So it's not on the training data, but on the test data. So if you end up doing research where classification problems are relevant, I invite you to try out gradient boosting. So if you want to have a test on your data for the cancer data and compare that with your neural network in project 2, if you wish to add more entropy to your project 2, you could simply mention that gradient boosting actually seems to be outperforming logistic regression, random forests, or best possible neural network code. And so when you do machine learning, you have to try different methods. And that's the standard practice because you don't know a priori which one works best for your data set. But gradient boosting is very popular, also because it's simple to implement and it's pretty simple to understand as well. Any questions so far? Is everybody convinced that gradient boosting is the method? I'm not paid by the people who wrote the algorithm, by the way.
I was thinking about how data quickly these methods are after the neural network methods we already discussed.
So on classification problems, gradient boosting does pretty well in most cases. and often beats a standard neural network.
But how data greedy are those methods?
Oh, so I didn't hear that. I'm sorry for that. Sorry. So the deep learning methods are data greedy. So these methods here are also normally data greedy, but not as data greedy as a neural network. They're actually less data greedy, gradient boosting methods.
So do you have like a tendency of where it starts?
No, I think you would have to try from case to case, actually. But in general, what you could say is that the more data you have, the better the situation is. And typically when you have very little data, you know, if you do a regression problem, like you saw in project number 1, you will often then see that there can be a delicate balance between outliers and not outliers. So if you have few data, if you have some outliers, they can actually ruin everything. So what I would say is that in general, all these methods are data greedy. The more data, the better. But what you could say now is that if you look at these methods here compared to a neural network, the number of operations you do are less. Because with a deep neural network, you have all these affine transformations where you deal with dense matrices being multiplied with each other. So that clearly takes a lot of time, and you have the back propagation. Whereas in this case, when you're looking at, let's say, gradient boosting, you have just a loop, a given number of times. You call a weak learner, which is extremely fast to calculate. Then you need to have the gradient of the cost function in terms of the function you want to optimize. And then you have an optimization in order to get the additional parameters. And this is normally pretty fast. So there is no need for back propagation and all that stuff.
So it's the gradient part that is...
Yeah. So like a neural network, I mean, is much more expensive to train than these methods here. Much more expensive. So there's always a trade-off here. My experience is that these boosting methods, they do worse on regression cases, the regression cases I've studied, than on classification cases. So they seem to do a pretty good job on classification.
Would you say that it's a trade-off between stability and computational cost?
Yeah, it's always like that. So at the end, you have to make a decision. So if let's say a ordinary least squares does the best job, and you are so deeply disappointed because all the time you spent writing a fancy neural network or deep learning code, and then you see that this old-fashioned ordinary least squares does a better job, clearly then there's a level of disappointment. But at the same time, you have to pick the method which does the best job. And if ordinary least squares does the best job, you would stay with that. On the other hand, when you have function which you don't know whether they are convex or not, whether global minima or the local minima are, then normally you would implement a deep learning method, because these are methods which typically would allow you to explore the space of degrees of freedom in a much more efficient way than the other methods. So the deep learning with the universal approximation theorem is actually a very, very important theorem, which states that you can actually fit a continuous function to a given error with at least one hidden layer. It doesn't say anything about the architecture and how many layers you have and so on, but with at least one hidden layer, you can fit nonlinear continuous functions. And I've seen it in my applications, which are physics driven, like when I solve quantum mechanical problems. There is an amazing flexibility and you get amazingly good results for many quantum mechanical expectation values. And I didn't expect that. And that has simply to do with universal approximation theorem. And then you may have other cases where ordinary least squares or regional lasso regression do a better job at a much lower CPU expenditure. So if I run, just to give an example, if I run a traditional quantum mechanical calculation for a given system, It will often, with a neural network, it will be a factor, a time factor in terms of CPU cycles, which is at least a factor of 10 to 100. So they are much more expensive to train compared to, let's say, a standard differential equation solver. So it's always this trade-off which you, at the end, have to make. But clearly, machine learning, as we discussed in the beginning of the semester, deals also with finding correlations in the data, which you perhaps could not find by a traditional method. So there may be features which you didn't expect to be important and which can be revealed by some of these machine learning methods because you let the algorithm explore a huge part of space which probably you would not be able to explore with a traditional method. So there are many pros and cons here, and I think we are just seeing the start of the usage of many of these methods to tons of applications. So this kind of cancer data application which we're looking at, there's another reason why I bring it up. It's not only because, I mean, breast cancer is an important thing, but it's also because we see one of the big areas of applications of machine learning methods, and also imaging in particular, is actually on analyzing scans of tumors or scans of body parts or whatever. And you will see like the Chinese company Alibaba. I don't know if you know that company, which is a kind of equivalent of Meta and Alphabet in China. They've invested a lot on AI and machine learning. And one of the reasons is that in China, they have less doctors per inhabitant than we have in the Western world. And when you run through a scan of tumors, for instance, this can take a pathologist 1 or 2 days. If you can just run a scan with a convolution neural network, which could take just a few seconds, and then flag the dubious cases, and then classify the other ones correctly, that is a huge benefit for society, because then the doctor can actually use time, or the pathologist use time on analyzing these specific tumors, which are the dubious ones. So this is extremely useful. It automatizes things which would take people a long, long time to study. And I think we're just seeing we're just scratching the surface of all possibilities. And I think by 2030, sorry for this digression here before we take a break, but I think by 2030, many countries estimate that innovation and actually even parts of the GDP, the gross national product, I mean, up to 20% will be dominated by AI and machine learning developments and applications. So that's I think this is inevitable. And as you've seen, I mean, you automatize many things which in a sense are not that exciting to do, right? So if the machine can learn some patterns which you wouldn't find, this is, to me, this represents a kind of progress, but you have to always to be critical, and you have to understand what goes into the methods. That's perhaps the most important thing. And one of the aims with this course is actually to demystify many of the basic ingredients. So when you run decision trees, you know that there is a human who has written the splitting of the tree. You have coded the Gini index, you have coded the entropy. When you write a neural network, there's a human who's actually written how this is going to be. And then you let the algorithm find the connections between different features. Okay, so after the break, we are going to, sorry for this ranting along a tangent, but it's actually useful to think of what many of these things mean and what kind of potential there exists in automatizing things, but also what kind of dangers exist. So we won't discuss these things in depth at all, but it's always important to know about, I mean, we put an emphasis here on the pros and the cons and the strengths and the weaknesses of the methods and what actually enters. So when you've written your neural network, you know that you could easily move on to write your own convolution neural network. You could easily write your own recurrent neural network if you're willing to just spend some time on it. Okay, I'm going to put the recording to pause, and then we just take a break, stretch legs, and feel free to ask questions. And we just start again in 15 minutes. So now we're beginning with what I've labeled as the last supervised learning method, which we're going to cover this semester. And this is a method which was actually introduced back in the 90s. And it has a very nice geometrical interpretation. So what we are going to end up with is an optimization problem with a constraint or several constraints. And when we have constraints in the optimization problem, we have to inevitably to start looking at what's called the Lagrangian formalism. So we are going to introduce what is called Lagrange multipliers, and then we are going to optimize a cost function, which is now just a slightly different from what we've seen before. So just think of what we're going to do now as a kind of Lagrangian optimization problem. And normally this leads to the whole battery of methods which are called convex optimization problems. Now, what I'm going to try to give you is a kind of overview of the basic ingredients. And we're going to try to start with a two-dimensional case, which is easy to understand, because that conveys much of the basic machinery behind support vector machines. So support vector machines are extremely popular as well. They're also easy to implement, and they normally give a pretty good result on both classification and regression. So let's try to take a look at them. As I said, these are convex optimization problems, so that leads to classical linear algebra, a field of linear algebra problems. So the support vector machines, as I said, they were introduced back in the 90s, in the previous millennium. And what it normally does, and the cases we are going to look at, are a binary case in the beginning. They were introduced in the beginning for classification problems, but then they have been it has been easy to extend them to regression problems as well. But we are going to look at a classification problem. And in the first run, we are going to look at a classification problem where we can separate well two classes of outputs. And we are going to classify the two classes in terms of output -1 and +1. So it's a binary problem. And then we are going to define something which is called, as you can see in the text here, something which is called a margin. And the margin is going to separate. It's the best possible way to separate two classes. So as I said in the beginning, we are going to look at a simpler case, and then we are going to move on to ways by which we can transform the data so that we can actually separate the classes we want to predict. And in that case, we need something which are called kernel functions, which are going to transform our data to an easier mapping where hopefully we can split two classes. But we are going to start with a case where we have two well-defined classes and split by a very easily defined by the eye region which separates the two classes. This leads to, when we move beyond just a plane, it's going to lead to hyperplanes. So if we just have a plane, then the separation between the two classes is going to be a line. And I'm going to try to develop your intuition about these methods by just looking at a two-dimensional case. And when we go to 3 dimensions, the area which separates the classes will be a plane. And then when you go beyond 4 dimensions or 4 dimensions and higher, it's going to be a hyperplane, which to me is difficult to visualize. I mean, it's difficult enough in 2 dimensions for me. And you probably noticed that throughout the course of this, throughout the time we've been together here. But I wanted to show you, here is just a data set which takes this petal width, and you can then define, so if you now look at the cases which we have, so this is given by the red line is a stochastic gradient classifier. So I'm running a logistic regression classification. This is a support vector machine classifier, where I have done some kernel transformations, but the linear one is the one which is of interest here. And you see now you have two classes in terms of petal width and petal length. And you see that these are well separated. And in this case, you could even use a linear regression to separate the two classes. The problem with linear regression is that the line could have different slopes. So you have tons of lines you could make in order to separate the two classes. So there wouldn't be a unique line which separates them. So what you often want to have is a unique way to separate these classes. So if you draw a line, you could have a line which goes like that. In this case, you could have a line which just the horizontal and still does the job. So when you're using linear regression here, you could easily fit this data set because this is a well-separated data set. Later, we are going to look at cases when the data are not that well separated. And with support vector machines, we actually have quite a lot of flexibility in order to separate different classes and make a decent prediction. But we're going to start with a case like this, okay? And I just wanted to bring up some definitions first. So normally we want to find a hyperplane. So in 2 dimensions, this is just a straight line. And normally you would have a p-dimensional space, but p is a number of features that classifies the data points. And in a p-dimensional space, a hyperplane is what we call an affine subspace of dimension p minus 1. So as I said, in 2 dimensions, a hyperplane is simply a straight line. And in 3 dimensions is a 2-dimensional subspace, or just, in plain words, a plane. Okay, so let's go back to the whiteboard and try to develop some basic intuition about support vector machines and how we actually set up this the classification between these 2 domains. So let me just jump back to the whiteboard. So what we're going to need now is plain vector analysis, nothing more than that, since we're going to be in 2 dimensions. So let's take a look at the data set. And when we did the decision trees, we looked at this data set where we had the average grade, which we got, or the grade which we got compared with the average grade. And we looked at how that was correlated with the number of hours we studied and the number of hours we slept. So you could now think of such a very simple case where we have 2 features, x1 and x2. So x1 and x2. And in this case, we are going now to assume that we have a pretty well separated data set. And here we could even think of just drawing a line and state now that the prediction we make, so the predictions which we are going to make, y of I, is going to take 2 values. So this is a binary case, -1 and +1. So above the line, the red line, we have a case where you get a grade which is above average. So you could say now that this corresponds, the crosses corresponds to y equal to +1. So you get a grade which is higher than average. And then you have the other class, which has a y equal to -1. And what you simply could say now is that this line here defines y equal to 0. So you would then say that, okay, if my prediction y is less than 0, then I give the value -1. If it's larger than 0, I give the value +1. So that's a very simple way to actually determine here. So you predict a line, y. This could be just a linear regression case. And then you simply say now that if my result is larger than 0, then I predict +1. If it's less than 0, I predict -1. So that's a pretty simple way by which we can use this data set. So let's now assume that we have defined our vector x, t, and this is going to be given by x1 and x2. So this is our vector. And then we define a new vector, w, which is a weight vector and contains the parameters which we want to fit. And then I have my W0, which we normally would call the bias, or we could call this the intercept if we just are thinking of a straight line here, right? And then what I'm going to do now is to write a model where I now have a y tilde of x, which is simply given by wt of x plus a w0. And if you spell it out, this is w1 of x1 plus w2 of x2 plus w0. So this is my model. In order to actually make this kind of prediction, so if my y tilde of x is larger than 0, I say my output is 1. If it's less, it's minus 1. So the input then is assigned to a class, and if this y tilde of x is larger than 0, then the result, the output belongs to class 1. To C1, and C1 is a case where y of I, the output which we're comparing with, is plus 1, and else, if y tilde x is less than 0, then we have C2, which then corresponds to y of I. So there are two classes in this case here, C1 and C2. So let's look a little bit more at the two-dimensional case. So we would also say that when this y tilde of x is equal to 0, that's when we are on the boundary. So with yx equal to 0, then we are on the boundary. Defines the boundary. Okay? So let's look at the kind of vector analysis which we can make here. So suppose now, or maybe somebody didn't get time to write it. So let's just make a plot of this. So we have the two domains. We can now think of x1, x2 here, and we have this line, which is our model. So we have y tilde of x, and here it's actually on the line, it is equal to 0. Then we have a point here, which we could call x of a, and then we have another point, x of b, and everything is related to an origin. And then we know that this point here and this point here, they obviously have y of xa is equal to y tilde of xb, and they are equal to 0. Okay? And then we also know that we can have another point, so we could have a point x here, and that would be defined by this distance from the origin. This case here would be the C1, where y is larger than 0. So now when I've don't put a tilde, this is not my model. And then I have my region C2 here, where y is less than 0. Okay? Then, if we look at these 2 points, so I have y of xa is equal to y tilde of xb, and they're equal to 0. So that means that if I now take the difference between the two, this is the same due to the mathematical properties of vector multiplications, and this is equal to 0, right? What does that mean with respect to w? Yeah? Yeah, let me do that. Sometimes I'm a little bit too fast here. Can you see everything? Yeah. So when you look at the last equation here, it looks very innocuous, but now these are vectors, right? What does it mean with respect to the vector w? Yeah? Yeah, so w is orthogonal. So that's a very important, and that's one of the properties we're going to use now. So W is then orthogonal to every vector lying within the decision surface. So the straight line, which you see here now, this is now, since this is just a line, but if we now think in 2 and higher dimensions, this is going to be a surface. And this is often called the decision surface. So that means that this vector, W, is orthogonal to every vector which lies in the decisions, within the decision surface. So the thing we want to do now is actually to be able to find these weights W so that we can make this separation here. That's essentially what we want to do. Now let's make a new drawing here. So what this W actually defines, if we now want to add a little bit more insights about the mathematics, so W determines the orientation of the decision surface from a chosen reference. In our case, this is just a line of the decision surface. In our case, just a line from a chosen origo. Reference or origo. So let's make a new drawing here and look at the case when we now have a point which lies on the line here. So if we now look at y of x equal to 0, this is the same as wt times x plus w0. And that means now if we normalize this vector, so we normalize wt, or the vector w, by calculating wt times w. This is the same as the norm 2 of the vector. So what I'm going to do now is simply to introduce a new vector, which is just normalized. So I'm going to divide wt with its normalization here. So what I'm doing actually, I'm dividing by w, the norm on both sides. So that means that when I look at this quantity as 0, I can rewrite wt of x divided by the norm here equal to minus w0 divided by the norm again. So when we now look at a general vector, we can actually construct a general vector in terms of this orthogonal vector plus something else. So let's take a look at another look at the drawing which we made previously. So we have x1, x2 here, and then we have this plane, in our case the line, and we have now a point x here, and we could now rewrite this in terms of a straight line here, which goes to the boundary, and let's call this x with a perpendicular sign. And then there is a small distance here, which we just call delta. That means that the final vector is actually this one. So just the sum of these two vectors, okay? So we would have x equal to, so this is a vector x, and I'm not putting things in boldfaces, but it should be clear from the context that these are vectors, okay? So this is going to be given by a parameter delta, which is just a multiplicative factor. multiplied with this quantity W divided by this W norm here. And why do we do that? When we now look at the vector W, it can look like this, okay? So we don't know where it ends. We only know that it's perpendicular to the decision plane. So if you now look at what you have here, when you go the straight way up here, this quantity here, what you could say now is that this quantity delta, what we need now is actually a delta times this vector W divided by the norm here. So what we have is a vector W, which is orthogonal to the decision plane, and we see that here, the way we made the addition. Is that clear? And then I simply have a multiplicative factor, which brings me from here to here, but multiplied with this quantity. So this is actually multiplied by this specific quantity here. That makes sense? So I have a vector which is orthogonal to the decision plane. And then I want to define a vector which is outside the decision plane in terms of this orthogonal vector times a parameter plus a vector x, which I call perpendicular, okay? Then what I know is that when I look at these quantities which I have defined, I know that this one is actually on the decision line. So this is my y tilde. So this has to be equal to 0, right? So if I then take and multiply Wt with this vector x, what I get then is obviously Wt times x, and this quantity x orthogonal, the quantity which lies on the decision line, and then I have a delta, and now I have multiplied with the norm again, divided, actually this is a norm squared, and this is a square root divided by the square root of the norm. So we know that that one actually has to be equal to what we will get on top here would be the norm 2. Now what we know is that the first quantity, if we now add W0 on both sides, what we get then is actually y of x is equal to Wt of x plus W0. This is the definition of the model which we have. And this is equal to the quantity we have here, Wt of x plus W0 plus this delta. And then what I have then is actually the norm 2 here, like that. Now, what I know next is the following. I know that when y tilde of x of t is equal to 0, that means that Wt of x plus omega 0 is 0. So that means that my omega t is actually equal to omega t times x perpendicular is equal to minus omega 0. So that means that in the equations which we have here, these terms actually cancel each other by definition. And what I'm left with then is the following. So I have a y of x divided by this norm of w, which is equal to delta. And in our case, this now represents, so I actually have a minus here. So this is a signed, normally called a sign difference. So if I now take a binary problem here, what I am interested in is to try to find this quantity W and the quantity delta. Now, before we do that, let's look at a simple implementation, which is not going to be that different from linear regression, but allows us to use what we have done till now, and defies a little bit the philosophy of many of these methods here. So we want to define a cost function which now contains all misclassifications. So before we use this result now, let's look at a simpler case. So this is an intermediate step here. Before we move on to the more interesting case. So this intermediate step is now us asking ourselves, could we define, or can we define, a cost function which now contains, like we did in ADA boosting, all misclassifications, which contains all misclassifications. And this misclassification points, and let's assume that there are, with a set now M, so there's a set M which contains all the misclassification points, and we want to minimize the error which we make, all the misclassification. So it contains all misclassification points, and we want to minimize this. To minimize it. Now, what we could do then is to define a cost function which depends on this parameter omega and this parameter omega 0. And then simply B, we have a -1 here because we want to find the minimum. And this is a sum over the points which now are misclassified. And what we have now is the result, y of I. This is what we want to reproduce. And this is multiplied with our function, wt of x of I plus w0. So you see now clearly that if I classify correctly, this is positive, right? Because then it's minus minus plus 1, or plus 1 times plus 1. If I misclassify, this becomes minus, and then I have a minus in front of it. And then I want to optimize this function. So this is an extremely simple function which we can set up in order to find out whether we are classifying correctly or not by putting emphasis on the misclassified results. So suppose now that we define y of I equal 1 as misclassified. So if y tilde equal 1, then misclassified if this wt of x of I plus w0 is less than 0. Sorry, this is the y, the real y. We have a y of I equal to 1. That gets misclassified if we get this one less than 0. And then we have the opposite if y of I is equal to -1. Then we would typically take the derivatives. So we calculate the gradients. So we have the parameter w0, and we want to drive that to 0. So if we look at the equation which we have here, this is simply minus, and then we have a sum over I element in M, the misclassified points, and this is y of I. So that's one of the derivatives. And then we have the other one, dc of dw. We want to drive that to 0. So that's going to give us a minus I of M of y of I of x of I. And then we could use our standard gradient descent and update the parameters till we have actually gotten rid of all the misclassified events. So the kind of learning which we would have here would now be with the gradients. We would then update this parameter here by w0 minus some learning rate times dc dw 0, and then we would do the same with this quantity here. minus and learning rate of dc of dw. So this is a very simple extension of what we have been doing till now, basically. Yeah?
What's the interpretation of the magnitude of the cost function?
Could you say again?
What's the interpretation of the magnitude of the cost function?
So you want this to be zero at the end, because you want to have zero misclassified results. That's essentially what you want. So you simply sum over all the misclassified ones, and that defines a number for you. And you want to drive that to zero.
You get positive when it's misclassified,
yeah.
negative when
yeah.
it's
right.
classified.
Yeah.
So
yeah.
why wouldn't you be able to just use the indicator function, for example, and then just use the signs?
Oh yeah, you could use that one as well.
Okay, but then my question is,
yeah.
how does the magnitude affect the results?
Yeah, that's a good question. I haven't thought of that yet. Okay, let me think of that. I don't have an immediate answer to it.
Yeah, I was thinking that in this decision plane, the points the further away will be weighted less than the points closer to the decision.
In this specific case, yes, because so that actually brings in an important point, because when you do this, your line can take many shapes, depending on where the misclassified points are. So if you look back at what we have here, if you fit a straight line up here, suppose you do just plain linear regression, this line can have different slopes. When you apply this recipe, which I put up now, you can also get a line with different slopes, depending on how you start your calculation. So that means that you are not able to uniquely define the border here. What you want then is a way to uniquely define the border. And that's where the support vector machines come in. So this algorithm here, which is pretty simple, and as you said, Johan, this is an algorithm where you can have an emphasis on points which are far away, and that can easily lead to, depending on how you do the optimization, it can give you lines which can have different slopes. So what we want to do now is actually to define in a better way a kind of demarcation land between the two classes. So what we want now, this can actually lead to different decision lines. And that's one of the reasons why you wouldn't use it. So what we are going to do now is something else. So we are going to, if we go back to the data set which we have, so we have an x1 and an x2 here, and then we have our points. This is the region C2 where y is less than 0, and then we have the region C1 where y is larger than 0. Now what we want now, suppose these are the, and let's mark these points in red. So we would now like to find a kind of border which separates the different planes, the different regions. So we have the x's up here. And as I mentioned earlier, this is an example of a case where the two classes are well separated. And then we have a line where y of x, the function which we are going to make, this y tilde of x, is exactly equal to 0. So this is this line. This line is now separated by the distance which is perpendicular to the line to the points which are closest in the two classes. So we are now using a point M. This is going to be called a margin. So what we want to do now is to define a barren land. It sounds like Mordor in Lord of the Rings. So where nothing exists, just waste. And this provides us a clear way to separate the two classes. Because when we have this midpoint line, we can have different slopes of it. And what we rather want to do now is to find a minimum distance to the points which are closest to this line with y tilde equal to 0, and then put a constraint that this is what is going to split the two lines. So the points which are on this line, they are called the support vectors. So when you run the calculation, you don't need to actually, in the classification problem, you are not going to store a fit which gives you a reproduction of all the data points, but it gives you only the data points which mark the margin M. So suppose you have 2 free points, you need only information about these 2 free points. And that is what defines your model, defines the margin. And then you would use your function, which you predict then, to actually use that on test data. And then you would simply say that if the test data says that you're beyond that margin, it belongs to one class, C2 or C1. So this is a way to, in a very strict way, to separate the two classes by looking at the points which are closest to this midpoint line. So this is the basic philosophy of a support vector machine. And the points on this margin, they are the points which define the support vectors. Yeah?
You said that you could have different lines with different slopes.
Yeah.
They have different support vectors.
They would have different support vectors, that's true. But in this case here, what you're trying to do now is to find a kind of middle way between several points. So if you just have one point, that could clearly depend a little bit on how you define your margin. But normally, with just one point in between there, it should normally give you a clear separation between the classes. So the whole philosophy is that you want to define a separation here, which is uniquely set according to the points which you have. So you're looking at the, you define a kind of midpoint here, but then you want to have points which are perpendicular to this midpoint line. So the definition of the points there is that these are perpendicular to the line, and you would take the closest ones. So when you have defined this margin M, you know that this defines a line in this case which is perpendicular to the decision line. And then when you have a perpendicular line, it means that this line has to be parallel to this line here. And you would do the same here, even if you would have points which could lie here and not on the line. Did that help in gaining some kind of intuition about it?
The line you chose to compare.
Yeah.
Like the middle line between the two closest points.
Yeah, yeah.
But what if you have like an X, say, way down there because
So this is a very important point because that leads to what's called a soft margin. So what you could have, and this is a very good question. So for those of you online, there is you could have points, these x's, you could have an x which is here, for instance. So what you can do now is to allow for a margin. So what you see here is normally called a hard margin. So that doesn't allow anything in between. But you could have points then which will be clearly misclassified. So you could now try to define something which is called a soft margin. So you will then allow for some points which can be misclassified. And this will be the next thing we are going to look at. So first we're going to derive the mathematics for the hard margin, where you don't allow for such situations. But then we can introduce some slack, and it defines a slack parameter, where you now can allow for a margin which is not that hard. But then comes another thing. You may have situations which don't look as nice as what you have here. So you could have a situation where you have points or circles here, circles there, so that it's much more mixed. In that case, what people normally do is they try to use what's called a kernel transformation, where by some smart transformations, you can actually transform your data so that you separate the two classes. So the cases I picked now was just for pedagogical reasons, a class which is well two classes which are well separated. But then the next step, when we still can deal with a linear separation, so this is a linear separation because the data look like they do, we are going to look at the case where we can introduce a slack in case we have points which are not within this clear linear separation. And then the next step is actually to perform transformations of the data set so that you can separate the two classes or the many classes you have. That's a good question. And so now I'm going to baby step you through the first step, which is the hard margin. Okay, so what we're going to do then is if we look at this quantity which we defined, so let's now bring this back. So what we are going to search now is something, we defined now this kind of parameter, which we call an f, sorry, not that one. So we define this delta, and I'm just going to give a positive sign to it. So we define that quantity in terms of this norm or the vector. And then we are now going to seek a margin. Which is so that margin M, which is defined by, so I'm going to now take my model and where I have my WT times an X minus an X0. And this is given by this norm, which I put in here, W2 times a WT of X plus a W0. And that defines this quantity. This is the same as f of X over W of 2. So X0 is just another point which lies on this line. And we seek a margin which is defined so that when I multiply y of I with this specific function, which now has been, where I've used this quantity delta to define the point, I now am seeking after this quantity here, WT of X of I plus this W0. And now instead of having this larger or equal than 1, because that would be a correctly classified quantity, I want this one to be larger or equal to a quantity M. So which is now the margin. Normally, what we had, you remember we had a y of I, and we multiplied that with a y of I tilde, and we want this one to be larger or equal than 1. Or actually larger or equal than 0. That's what we want in general. So if we didn't define a margin, this is what we want to have if things are classified correctly. So now, instead of having 0, we are going to put this value M, this margin here. That means that when I now look at my vector, so remember now that we could rewrite the vector in terms of this norm, of these weights. If I look at my constraints here, I can now rewrite this as a y of WT of X of I plus W0. And this is going to be larger than M multiplied with the norm here. Now, what I'm going to do now is just to state that I can choose this quantity to be so that it's larger than or equal to 1. Next week, I'm going to show a theorem which actually shows that this is correct. But the quantity which I have here, I can now simply choose to let this quantity be equal to 1. So that means that what I want now is a margin which is equal to 1 over this quantity here. And then next week, I'm going to show you that you can actually define a theorem which says that this quantity has to be equal to 1. Now, if you decide for that, so what we're saying now is that M And normally we want M to be as large as possible. Why do we want it to be as large as possible? By the way, I should ask you that question before we move on. Say again? Yeah, because if you make M small, then you're back to 0, right? So you want to be this the largest possible so that you can well separate the classes. So the kind of problem which we are going to deal with now is to find an M which is the largest possible, which again means that we want the norm to be the smallest possible. So what we could do now is actually to set up an optimization problem where we want to maximize M or we want to minimize the norm, right? So either way, and what is normally done then when we are setting up the problem is to minimize the norm. And when we minimize the norm, so what we're going to set up, and I'm going to just sneak in one more minute here, and then next week we are going through the details and we're going to set up the problem and we're going to remind you about Lagrangian multipliers because this becomes a Lagrangian optimization problem. Does that ring a bell? I guess you saw this basically in one of the first mathematics courses, right? On the Lagrangian optimization problem. I'm going to refresh your memory, guys. I see that. I see from the faces that there's a need of a reboot of the memory here. But what we will end up with is a minimization with respect to the parameters W and W0 of the norm. We can maximize the margin with a constraint. The constraint that y of I multiplied with Wt or y, no, x of I, sorry, of x of I plus W0 is larger or equal than 1. And this is the kind of constraint which we are going to rewrite in terms of a Lagrangian. So we are going to get more variables which we need to optimize. So this is the basics of support vector machines. Now here we have a hard margin, but we can make it softer, and that leads to a new parameter, which is normally called the slack parameter. And then if this kind of clear linear distinction, which we have seen now, doesn't work, then we can look at kernel transformations. So essentially, we end up with a convex optimization problem. And this is the kind of stuff which we are going to detail next week. I'm also going to send you guys an email, whether there's an interest in having a workshop next week, preferentially next Friday, where people present possible paths for the third project. And what's normally happened is that some people listen to the presentations and say, hey, I like this. I would like to join the group. I would like to work with you, and so on. And it's also a good way to see all the possibilities which exist with machine learning, the way we've been teaching till now. Okay, so next week, it's more details about support vector machines, and hopefully we can have some time for a kind of mini workshop with you guys present possible alternatives for project number 3. So you will receive an email together with also project number 3, either tomorrow or early Sunday. Actually, many of you don't read my emails. Okay, guys, have a good weekend. Take care.